So I'm going to start, first of all, by talking about why we might reconstruct past stream flow. I'm going to be talking about the Klamath River and using true rings to reconstruct that. And I'll first start by saying, why would we want to do that? I'll then talk a little bit about the process of reconstructing and some of the challenges that we have with data uncertainties and data imperfections. And then given imperfect data, not a true record of the past, what's the most reliable information that we can get from these reconstructed past flows? In particular, what does the reconstruction of the Klamath tell us? Now, I'm going to be using examples that I have just pulled out. There's a lot of ways to look at this information. There's a lot of ways it can be applied. So hopefully you can all think about those different ways and just consider what I'm showing you as examples. So historically, compacts, water policy management have been based on the available records at the time. And so I'm going to give you an example for the Colorado River. That's been a focus of a lot of my work. But here's the record of the Colorado River at Lee's Ferry from 1906 to 1930. These are annual flow in million acre feet. The light line are annual values. The blue line is smooth. And this was more or less what the record looked like to the folks that negotiated the Colorado River Compact in 1922. And they took a record in 1922 that looked a bit like that, and they divided it into two. They divided it into flows for the upper basin and for the lower basin. They allocated 7.5 million acre feet for each basin. Now, as time has gone on, that record, the record that the allocation was based on, looks to be a little wetter than it typically has been after that period of time. So it's been evident that the allocations, those set amounts, not percents, but set amounts, were based on a wetter than average period of time. Now, the question is, we have 100 years or so of record, which is a pretty long record in some perspectives, but it is only 100 years, and is that record really representative of the flows over a longer period of time? So we can look at the true ring reconstruction of the Colorado River down here, which goes from 1490 to 1997, and assess this record in the longer context. And we can take a look at that period that was wet in this context and see it actually is a pretty anomalous wet period when you go back about 500 years. And so this certainly has implications for the over-allocation of this system. And this is something that we're dealing with in the basin right now. So the Klamath Basin is pretty different than the Colorado River Basin. Colorado River Basin is in the southwest, arid area, snowpack driven. Here's the Klamath headwaters in Oregon, flows down through California. They're pretty different, but there's some similarities that could allow us to apply this sort of usage of the reconstruction in the Klamath as well. In both cases, the demand is often greater than the supply, and there's some obvious news recently that indicates that. Here's a headline from August 17th that says, Feds cut Colorado River releases. CAP, which is the Central Arizona Project, shortage risks increase. And what they're saying is that they're reducing the flows from the upper large reservoir Lake Powell into Lake Mead, and that has implications in a year or two for the amount of water that Arizona might get. It's sort of foreshadowing the potential for cuts. This is a headline from August 23rd. Judge okays water releases to help Klamath salmon. Federal judge late Thursday allowed the government to release water into the Klamath to protect spawning salmon, saying the danger of a major fish kill outweighed the loss of irrigation water to Central Valley farmers. I'm sure you are all pretty well acquainted with this issue, but in both cases, the judgment is being made where we're going to allow water for this use or these folks based on laws or negotiations, and we're going to cut these uses because there's not enough water for both, especially in times of drought. So how can these records from the past help us plan for a more robust future? There's a lot of different ways that the reconstructions of stream flow have been applied to management questions, and I'm not going to talk about the specifics of them. There's certainly ones that can be discussed, but I'll talk about two general applications. The climate change and water resource management, a federal perspective, it's a multi-agency report, and the reclamation's Colorado River Basin supply study. This is too small to see, but in the table of contents for both of them, they have sections about how the paleoclimatic record, the true ring record in particular, is being used, oftentimes in combination with projections for future flows. to develop scenarios for the future. What could the future hold? Well, we have information about past long-term natural variability from the treeing records that's not going to go away because we have climate change, and we can combine that with historical flows and projected flows to produce these scenarios, these possible future flows that we could use for planning. So that's one example of how this information is being applied, and there's many more. Okay, I'm going to talk a little bit about reconstructing streamflow. I'm not going to go into the details of the techniques, but just some general things. When we reconstruct past streamflow, there's two main requirements. We need old trees to give us long records that record moisture variability in their ring width. So when you have a dry year, you have a narrow ring. When you have a wet year, you have a wide ring in a climate region of interest. This is a western juniper from Bowles Creek, which I put 2 L's in, there's only 1 L, which is up near it's in California on the border with Oregon. These western juniper are very moisture sensitive. They have very good records of moisture variability in their ring widths. They grow to be very old, and they are sensing mostly the hydroclimatic conditions over the winter, the cool season. The trees are sort of going on the moisture in the soil at the beginning of the growing season. The other thing we need is a gauge record of interest that reflects natural flow conditions at least 30 years in length. And we need 30 years in length because we're actually calibrating the annual ring widths with the annual water year stream flow in our reconstruction model. So we need that overlap, and we need a record for our calibration. So for the Klamath, we have several records. We have the USGS gauge record, continuous from 1930 to 2012. We have estimated natural flows at Kino. And I should say that we're focusing on Kino because that seems to be a gauge that is of interest to management. Estimated natural flows from 1949 to 2000. And then we have relatively undepleted USGS gauge records for 2 of the major tributaries of the Klamath, the Williamson and Sprague Rivers, Nilchilliquin, from 1924 to 2012. And so our question is, what record is closest to reality? What's the best record for using to calibrate with the treeing data to do a reconstruction of Klamath flow at Kino? Well, we don't know which record is the right one or the best one. Here are the 3 records plotted together. They're not very different. The green line is the natural flows, and you can see they don't peak as high as the Kino USGS gauge or those 2 tributaries. The mean is lower for this record. There's reasons that they're different. This is a little bit hard to see, but this is a cartoon that's showing a conceptual model of natural flow. So it has all the inputs and outputs. Here's the Sprague River, here's the Williamson River. They combine and flow into Lake Klamath, Upper Lake Klamath. So those 2 records won't have the effects of evaporation and marshes, evapotranspiration. The Kino gauge is down here. So that USGS Kino gauge is going to have the effects of irrigation, all the outputs, some of the groundwater pumping, so it's not really going to be reality either. It's deficit. And then the whole thing was considered, the whole system was considered in the estimates of natural flows. And from what I've read, there's some contention about these estimates of natural flow and whether they actually are replicating reality. Well, we don't really know what reality is. So for the work that we've done, we went with the estimated natural flows. Understanding that, we're not sure if that's really what's really happening at that Kino gauge, but for a lack of more information, that's what we've used. So this is what the reconstruction looks like compared to the Kino natural flows in red, the reconstruction in blue, and you can see it's not a perfect match. We're explaining about 61% of the variance with a treeing model in that natural flow record. In particular, we're not getting some of these higher flows, but that's the model that we got from the tree rings. So given the less than perfect reconstruction of past flows, it's less than perfect because we're not sure if we actually used a gauge record, which is entirely accurate. There's problems, well, not problems, the reconstructions are reconstructions. They're not true flow. A tree is not a stream flow gauge, it's not a rain gauge, so it's not going to be perfect. Given these uncertainties and imperfections, what's the most reliable information that we can use from this reconstruction? Well, we can say what's not going to be reliable. We wouldn't probably trust the high flows in the reconstruction because they're biased low. But what might we trust? This is my barcode diagram. It's a barcode of dry years, so all the blue bars show the dry years. These are below average years from 1949 to 2000 baseline. The record are all going from 1930 to 2012, except for these start and ends are. We've got the two major tributaries, the USGS gauge at Keno, the Keno natural estimates, and the reconstruction. And you can see they all vary somewhat, but they tend to agree in general in sequences and runs of these dry years. And so for this exercise, I'd argue that this is maybe some of the most reliable information that we can get from the reconstruction. There's more agreement among the different records in terms of sequences of wet and dry years, runs of dry years, and so that's the information that I'm going to look at here. So here's just one example, comparing the Klamath at Keno US gauge record with the full reconstruction that goes back to 1493 and up to 2010, and I'm just showing you the driest 10% of years for the two records. So if you know this gauge record at all, if you know the climatology of this area, we're looking at a cluster of very dry years in the 1930s, 1991, 92 I think was the driest year in this whole record. This is 2005, which shows up in this gauge, but I think 2001 was really the marker year that stands out in the last 10 years. And then here's the full reconstruction. So you can see this is pretty well represented in terms of the gauge record and the reconstruction. And then what we can see going back in time is that the pattern is really irregular for these really extreme low flows. We've got a 1930s cluster. We have an even bigger cluster in the 1660s. In general, these extremes, low flow extremes, seem to be most predominant before about 1660. There's big gaps of years where we don't have any of these extreme low flows. So this is one way of placing this record in a long-term context that's looking at the fairly robust lowest flows in terms of the 10% lowest. Here's another way to look at the reconstruction. This is what I'm looking at, sequences of high, low, and moderate flows for the full period by century, 1500s to 2000s. The blue are the wettest third of the years, the orange are the driest third of the years, and the yellow ones are the ones that fall in between. So on each rectangle here is a single year. So we can see runs of dry years like the 1930s. There's another run in the 1650s and 60s. We can see shorter runs, but sequences of years that were wet. We see some back and forth where we go from the wet to the dry category, but in general we seem to see sets of wet and dry years in this record. And that turns out it's a characteristic of this record, of the stream flow. This is another way to sort of examine that particular characteristic. So here I'm asking the question, given a high flow year, so that's a year above the median, what's the chance that the following year will have a high flow or a low flow, be above or below the median? And conversely, if you have a low flow year, what's the chance that the following year will have a high or a low flow? So these are 50-year periods. This is probability. The red and the blue are the probability of going from a dry to a wet year or wet to a dry year. The orange is the probability of going from a dry to a dry year, and the blue is from a wet to a wet. And over the course of the reconstruction, we don't see a lot of variability in terms of one 50-year period to another, but the message here is that there's a much higher probability that a wet year will be followed by a wet year and a dry year followed by a dry year than we have a wet to dry or dry to wet, which suggests there's persistence in this system. And the question of where that persistence is coming from is an interesting one that we haven't pursued. But there's persistence in this system, and that's something probably managers may already be aware of, but want to know that it's, perhaps that it's been that way for quite some time. So another question that maybe is more interesting is if we have two high flow years in a row already, which we've seen the probability of that's pretty high, what's the chance that the third year will be high as well? Or given two low flow years, what's the chance that the third year will be low as well? So a 3-year sequence. And if we look at these in 50-year chunks, we can see it really is more variable across the full record. If we look at the last half century of the 20th century, you can see there's a high probability that 2 wet years will be followed by a third wet year. Less of a probability that 2 dry years will be followed by a third dry year. In the first half of the 20th century, you can see there was a lot of persistence, a lot of these 3-year sets. This is the 1930s drought, and this is the wetter period that occurred before that. Just in contrast, if we go to this 50-year period, a very high probability of persistent drought, not much lower probability that we see this persistence in wet conditions. And then this 50-year period where there's a lower probability of these persistent wet and dry conditions than in other 50-year chunks, saying there's probably more variability from year to year. So 3 take-home messages here that I hope that you'll come away with. One is that tree rings provide a longer-term perspective on the range of natural variability that's possible. This natural variability isn't going to end because we have climate change. It's going to continue on with climate change superimposed over it. Understanding data imperfections, and this isn't just for tree rings, but probably for anything else. It's good to understand the strengths and the weaknesses in interpreting the data. So keep that in mind. For the Klamath River in particular, the reconstruction suggests that periods of high or low flows are an inherent characteristic of this system. Looks like that's how that record is, or that river has. That's how the river has been characterized for some time. But those periods are distributed unevenly through time. So those are my sort of 3 take-home messages. I'd be interested, especially from the management people in the audience, but also the scientific people who are doing maybe not climate or not hydrology, but maybe there's other applications of this information. I'd be interested to hear from you about how this record might be useful to you. And I'd be happy to answer any other questions as well. Thank you.